Fantastic. Well,
Great.
hello everyone. Thank you for joining us in another machine learning launch seminar at Vanderbilt University. Today, we are very excited to have Daniel Moyer, one of our own, to give a talk on invariant representations. Daniel will be joining our computer science department this fall in 2022. As an assistant professor. Before joining Vanderbilt, Daniel was a postdoc in CSAIL at MIT working with Professor Polina Golland on fetal MRI images. And he received his doctorate in 2019 from University of Southern California under Paul Thompson and Greg Versteeg, where he worked on representation learning problems in diffusion MRI and neuroimaging. With that, Daniel, the stage is yours. We look forward to hearing your talk.
Thank you, and thank you for having me. So let me know verbally if there are any sound issues, because I don't have the chat pulled up. Feel free to post things in chat, and then hopefully somebody will interrupt me if you have questions. Yeah, so about half of these slides, perhaps some of you have seen before, because I gave a talk here in January. And it will look a little familiar, but today we'll actually be going a little deeper. So we're going to go on a deep dive into one of my favorite topics, which is representations using autoencoders. Instead of just the large survey that we did in January, we're going to get into the math, but I hope that it will be very helpful and interesting to all of you. Just seeing what's going on. If you do get bored, however, you can watch the yellow bar progress across the screen from left to right. So that will tell you exactly how far along we are in the slides. Great, and that's up at the top here. So previously, a little bit about myself. I worked in neuroimaging, so neuroscience, and I've also done work in machine learning and medical vision. And we won't see all of these things today, but we'll definitely, like, if you have interests in other topics that I've worked in, I'm still happy to talk about all of them. This is by no means like the narrow focus of my life today. I still think about a lot of these other projects. So that's brain connectivity or connectomics, parcellations and neuroanatomy, and fetal imaging. And of course, I have a plug for my own class this fall, which is CS 8395, one of the topics classes about things in this seminar today. So yeah, and there's still space, so that's great. Yeah, so today we'll actually only be talking about the second half of this, the machine learning and medical vision, and we'll mostly be talking about the machine learning portion for this as a machine learning seminar. Great. So so invariance. So this is the main topic today, and then we'll dive into vignettes around it. So in machine learning, we often have these prediction problems where we take in data, here MR images, and we want to output some phenotypic variable. So this would be healthy or diseased, some pathology, or we want to output endophenotypes, or what have you, right? Some label. But maybe less often discussed is the collection process. So alongside these, alongside the actual data that we put in, the image or the clinical information, we have the site or the scanner. And in regular images, we don't really think about the camera very often because there are so many cameras out there that we can't even track it. And perhaps it doesn't matter because our data set is so heterogeneous that we've seen a lot of different types of cameras. But in medical imaging, well, there's just not as many MRI scanners as there are cameras in the world. There's something like 1 billion cameras digital cameras that have been made by humans, right? There's one in every cell phone, so that's a lot. And there's something like 100,000 MRI machines by my own estimates, just the first order. So yeah, that's a very large difference in the number of machines and the regularity of the machines. We're taking pictures with a giant magnet. So this heterogeneity is actually very similar to other heterogeneity in images, though, that is more general. So here, we want to classify into cat and dog, so it's a little less clinically relevant, but there are definitely confounders in these images that we can think about. So here, we know that the label cat or dog is invariant to the pose of the cat. So if I rotate the cat, maybe you'll be upset, but it's still cat, right? And so we want to impose this invariance, like the rotation example, but in medical imaging. And also there's been interest in this, imposing these invariants, these symmetries in algorithmic fairness. So we want to be invariant to different demographic choices. And there it's not really a data symmetry, it's that we want to impose it. We want to force this to be true. Great. So how should we do this? Could we just ignore it? If we do ignore it, then our predictor, so here we have a predictor py given x. If we do ignore it, then if we go into a new scanner, our predictions will change based on the scanner. And we know that to be causally backward. Right, so we can try and model it. And this is actually how most people do it in statistics. They try and regress it out, right? They add control variables. And this is great for statistics and things like mixed effects models and these hierarchical models, but it doesn't generalize to new scanners. So if we add a new pastel colored ball at the bottom, then we won't be able to add this in our modeling because, well, it's not part of the model that we fit. So instead, what we could learn are latent factors. So now a non-pastel colored ball, a non-colored ball Z, that knows nothing about pastels, or that knows nothing about the factors that we want to remove. Great. So in rotation, this is pretty simple, or conceptually easy at least, that we want a representation of cats that doesn't include rotation, or dogs, right? And if you're more familiar with group theory, this is the quotient operator, right? Or maybe physics, like we want a representation that's equivariant. But that doesn't really work when we want to force this to be true and we don't know the group operation, or worse, there isn't a group operation, right? That we can go to different standards or different demographics and not have the same information be present. So there isn't really a nice quotient operation to bring us to a stable orbit, right? We can't collapse all those orbits. One alternative is to find representations that are independent of the thing that we want to remove. But this is a really harsh constraint, right? It's an independent constraint, so it's very fragile. So to relax that, we can move to mutual information. And this is where we're going to stay for the entirety of this deep dive. We're just going to talk about mutual information constraints on representation, and good things and bad things about them. Great. So now we have a little bit more information here about what's going on. So if we take our data and we send it to a representation through an encoder, so that's QZ given X, we want a latent factor that has minimal mutual information with the thing that we want to remove. So minimal IZ given S. And then guaranteed by the data processing inequality, basically we can't regain any information about S if we removed it from Z, right? So anything that we do with that Z is then also S independent, or at least up to how much we minimized IZ given S, or IZS, yeah. So this is the general setup and what we want to do with it. So what we need is a way to minimize mutual information between encoding variable and confounding variable. So we need an upper bound, right? We want to minimize mutual information. That's a little weird. Usually we always want to maximize mutual information in machine learning, but here we want to minimize it. So I know that in the previous talk, I skipped right through this math, but we're going to dive into it. Don't be scared. It's actually not that bad. So first, we're going to break it into the tripartite mutual information breakdown. So this is the three-way Venn diagram, if you've ever drawn that out, right? So it breaks into three mutual informations but the last one of these is actually 0. So z given the information between z and s, the encoding and the confounder, given x, well, z is an exact function of x. So given x, we don't have anything more. So that's 0. Great. Got rid of one of them. And of these two terms, well, we can break it down into this identity for entropy. And one of these is constant. It doesn't include z at all. It's the natural world's entropy of x given s. That's the second term here. And then this third term actually looks very familiar. It's the reconstruction term, right? So it's how well we can predict x given z, also known as conditional reconstruction. And that's it, actually. That is a bound for mutual information. So the important part of this is really this intuition that we have a compressive term, the information between z and x. So we want to somehow minimal representation, but we also want Fidelius reconstruction, good reconstruction. And then there's also a constant that's given to us from the universe. And yeah, this is how, this is one way that we can bound the mutual information. This bound is actually tight. So if we can do reconstruction perfectly, or as best as possible, right, we actually have the mutual information exactly, which is pretty cool. Not most bounds are actually not tight, right? And importantly, this becomes an autoencoder. So even though we were just doing math off on our own, we have an encoder structure, qz given x, and we have a decoder structure, which is actually conditional, or yeah, conditional decoder structure, px given z and s. So we can parameterize these using neural networks, right? And that's what we'll do. That's the first thing we'll do, is turn this into a neural network. So this is the canonical autoencoder picture, but with a conditional part. And then there's a compression term on z. Yeah. And it looks exactly like a VAE, or very similar to a VAE, at least. So here we can pull a trick. Changing the s variable will actually change the conditional reconstruction. So the first thing that we can do with it is just play a style transfer game. We can encode things and then make the encoding invariant to whatever style we have supervised, and then change that style on the way out. So if we do this with everyone's favorite data set, MNIST, we'll encode digits into stylistic digits without their digit class, without the number, and then decode them into all the rest of the digits. So we can take this 6 or this 9 into every other digit, and it looks somewhat similar. The decoder is not particularly strong in this case, so you see some interesting digits, but you get the idea, right? This one's very thick, and the thick gauge continues throughout. Great. So we can do style transfer with it. How does this relate to neuroimaging? So between scanners, we now want to create a harmonized scanner or a harmonized data set that doesn't have site effects. So we can create this same autoencoder, and this one's a little bit more complex because it's for diffusion data. We won't get into the details of that, but it's basically an autoencoder. And we'll train it on the regular site data. So this doesn't require supervision between sites. Again, we're training it with the site unmasked, right? Unchanged. We haven't tricked anyone, and creating an autoencoder that way. And then at test time, we'll choose one site, our favorite one, and we'll map everyone to it. And so hopefully at that new site, everyone has the same site-wise effect. So our downstream task that uses Z can't overfit the site because they're all the same. Right. So
Daniel, there's a question in the chat. Yikun had a question. Yikun, can you unmute and ask the question?
Oh, sorry. I just want to know in the beginning why we want to introduce variable s.
Okay, yeah. So I can pull up chat now. Oh, great. Yeah. So why the variable s? It is the variable that we want to remove. So we knew about it beforehand, right? if we don't know about these confounding variables, or we just don't have supervision of them, then we can't introduce S. So you're right.
You want to remove some information from your original data.
Yeah.
Is that correct? But S is not confirmed data.
No, we have to observe it. So it also has to be in our data set.
Okay.
So in this case, like we can imagine collecting MRIs from different hospitals, and we knew which hospital each image came from.
Okay.
Does that make sense?
Okay.
Yeah, so David Wang says, so can S be some sort of prior knowledge that we know, but the model does not? Yes, we want the model, or we want the encoding model, Z, not to know about S. But in the training set, at least, we have to know where each of our data points came from. There are variants of this where you try and learn S, but then you have to assume that it is actually that it actually has a symmetry, right? If you want to force it to be invariant, but the data set doesn't actually permit that, like in algorithmic fairness, where you want to force everything to be invariant, then it's hard to learn such a variable at the same time. Any other questions? Yeah, feel free. Yeah. Okay, we'll keep going then. So this is from the previous time that I was talking, but basically we have the CDMRI challenge data set. So for those of you who like diffusion imaging, this is a good data set. There's a great one from Vanderbilt, from Bennett Landman's group here that supersedes this, but this is another one where we have traveling subjects, and we're not using the correspondence between subjects, basically. We're using that just to validate things. Right, so compared to previous, compared to non-deep learning, non-harmonization, or linear harmonization methods, essentially, we're outperforming them greatly. So that's good. Linear here is actually a sort of a misnomer. This is a, essentially it's a linear effects model per voxel. So it has more parameters than our entire neural network, which, yeah. So again, if we look at the error plots, we want these to be all uniform, and you can actually see a brain structure here. You can see the white matter patterning. So that's really bad. That means our harmonization has different error rates based on the tissue type, which is not good. Here, instead, we only see the CSF, which, yeah, that's what we want to see. And if we try the multi-site version, we still get some white matter patterning, but it's better than the previous version. Yeah, and I've lost my chat, but I thought I saw something. Oh, okay. I'm sure somebody will interrupt if there is chat. Yeah. Okay. So yeah, this has been the fusion part of it, but really this compression term is a pain. And this is again, we're going into the deep dive, so we're going to go all the way into it. This is the mutual information between Z and X, also known as the mutual information between Z given X and the marginal QZ. But we never know QZ, right? Like we just defined this encoder, QZ given X. So the actual marginal, the empirical marginal, is complicated, right? We have to integrate over a data set, which is never a good time. So instead of that, what if we use the wrong compression? What if we use PZ given X, or PZ, sorry. What if we used a prior belief about it? And in an autoencoders, in this form of VAE, in Gaussian VAE, this turned out to work out pretty well. So in the first column, the oracle, the best you can do. In the second column, the correct compression. And in the third column, the conditional VAE compression. And for most cases, they're really close, right? So this tells me that the intuition behind our bound is almost as strong as the actual mathematics of our bound, at least for this case. And that's a really good thing, because PZ, the KL divergence between QZ given X and PZ is much easier to compute. But let's get into that. Why is that true? Or why should this be true for VAEs, for Gaussian VAEs? Right? We're thinking this. So this is the derivation of bound again. We're thinking, why is this accurate? And it's because we're using a Gaussian VAE, so the codes should be Gaussian in the first place. So if our encoder is no longer a Gaussian VAE, or alternatively, our data set makes the Gaussian VAE not generalized or not actually fit the prior very well, we're in trouble. So instead, well, okay, here's how we would compute it if we really wanted to grind away at it using Gaussians. And it's ugly. And the point of the slide is basically, this is not a good bound, right? This is not a good way to go about things. So instead, can we find a closed form for the mutual information between the code and the input? And it turns out that you probably can't do this with Gaussian VAE, with Gaussian encoders. We never proved that you cannot do this. So if someone's very clever, maybe they can come up with a way to do it, but it will change by encoding scheme. So instead, what if we redefine the noise model? So instead of using a Gaussian encoder, what if we use an encoder with a different distribution? And so this is from our 2019 paper by Rob Breckman and one of my collaborators and I. And yeah, so we have the same setup where we have a mean and something like a variance that we're adding together. So Z is the sum of f of x, a deterministic function, and s of x, another deterministic function, times epsilon, where epsilon is noise. But epsilon here is drawn from Z itself, the distribution of Z, which is a recursive definition. So here, Z has no closed form distribution, but it turns out that the mutual information will, and we'll speed through this, but basically, well, we can do the same breakdown, and we know f of x is deterministic, so that doesn't change anything. So we end up with entropy of Z minus entropy of Sx epsilon given x. But given x, we can move this multiplication outside, and now there's no dependence on x. And epsilon is drawn from Z, so these are the same term. So it's actually just the determinant of x, of s of x, right? So this is an exact rate distortion term, or an exact information term. And it sort of points toward the more general literature about the VAE objective itself, that if we allow ourselves to move past the prior modeling, the belief that there are latent variables in the world, and instead move toward the idea that, well, we're just constructing a code of what the world is, that yeah, that there's interesting results to be found here. So basically, moving away from the Gaussian priors might have interesting events or interesting results to come by. More about this in a class this fall, just a heads up, that we'll be talking about this and information bottleneck in context. But these ideas have been around for a while, so they've been hanging out in beta VAE by Irene Higgins, and also in the Olemi works, bottleneck and fixing a broken elbow. So yeah, there's some very interesting things going on there. Are there questions at this point about what's happening? This is a little weirder. And let's see.
Could you go back to the previous?
Yeah.
Okay. Here, Sx is a function of x. Is that right?
Yes.
Then when you compute the conditional entropy given x, Sx should be determined. The conditional entropy should be negative infinity.
No, because epsilon is not determined.
Oh.
Yeah, but you're right that this is a constant relative or given x, right? So yeah, that's why we can take it out of the entropy. And I kind of hid the fact that multiplying something essentially turns into a determinant for multilinear things. But yeah.
Okay. Oh, thank you.
Or yeah, linear transforms. You want to look at the volume change of that linear transform. But the only stochasticity left here is epsilon. And so we end up with just epsilon given x, but epsilon isn't a function of x, at least not this copy of x. So
Okay. Oh, thank you.
Yeah.
So I have a naive question, Daniel, right? And it's with respect to evaluation of such an autoencoder, right? So if you change S, you're going to reconstruct MRI images based on different scanners, right?
Yes.
Do we have the ground truth from the same subject under different MRI images? Is that like, how do we evaluate if we are reconstructing the right image based on that?
Yeah, so
New
this
scanner.
question is back here in the MR case, and here essentially in this data set we have sent 15 people to each of the scanners, and we just have to assume that their scans should be the same across time. That's quote gold standard data. One, it's very expensive, and
Right.
two, it's not actually true, because diffusion, your brain scans will change based on time of day, for example, sleep patterns, caffeine intake, things like this. So
Right.
yeah, so the answer is you're right. These are not, they shouldn't actually be the same, and that there's confounding between the subject signal, so what's happening with the human, and the magnet signal. There's not really a good answer to this unless we really did a lot of physics about the scanner, and also if we measured those measurements from each scanner. So if we did like magnetic field readings. Most hospitals, of course, do not do that.
Right.
Most research clinics don't do that either, or at least not in that like complete way, right? So yeah, I think for now, for humans at least, the gold standard really is traveling subjects. In mice or other in other animal models, we could assume that there would be clonal versions, so that they would be actually very similar. Yeah, but it's a hard problem to trying to validate this, and we can determine how much information is left by the prediction error, but we can't actually know if they really should be the same or not. Yeah.
And a follow-up question on that, right? So if the encoder was besides Z, it was actually predicting an S, and everything is the same, right? Like the encoder is predicting Z and S, and we still want these to have minimum mutual information, right? And then like you change S and send it through a decoder. Of course, you're going to reconstruct some other scanner, but then you can check the consistency. You can send that back. Right,
yeah, you can do a cycle loss.
Yeah, exactly, cycle loss there. So would that help, or like has anyone looked at that?
Yeah, so there was several papers, I guess, in recent years about doing cycle consistent loss, or the StarGAN style loss, which is essentially cycle consistent loss for multiple sites.
Right.
It does work. A lot of those were done in an adversarial case, which is the next section. But I think it's hard to guarantee that the latent space won't start to separate without us knowing. Essentially, we have to have an adversary. So this breakdown table here,
right,
where we're training an adversary after the fact to try and predict S from Z. This is the best validation for knowing if you have an invariant latent space. Yeah, so this has to be done, but then the problem is, okay, but how do we parameterize the adversary, right? Or do we overfit the adversary, or things like that? So there's another estimation problem at this point, and most of the papers don't really care about this. They just want to see that the resulting image, so the X's, all match up, because they have that gold standard supervision. So at least in our little experiments, it seems to work. But yeah, you're definitely right. And if we do this for fairness, like a different domain, things could be very bad. So we should check at this stage, and then have endless arguments about how to parameterize our adversary. Yeah.
Thank you so much.
Yeah, no, this is great. Other questions? Otherwise, we're gonna okay.
Based on your new model, you introduce noise to the encoder. Is that right?
Yes.
So it means that if you have fixed data, based on the new encoder, the embedded random variable, the embedded variable is not fixed because you have randomness from the noise.
Yes, although the noise will be fixed overall, that the S variable, maybe this is a good version of it. Yes, this S variable will always be the same. So the amount of added noise and the distribution of the noise will be the same.
Oh, okay.
Yep. But you're right that you would want to average this over a large number of cases. Yeah. Okay, so adversarial versions. So another way of doing this, and actually a much earlier form of doing this, is to put an adversary at the Z layer, right, at this bottleneck layer. So here we have the encoder decoder from last time, and then we'll have a prediction branch now. And secretly we had this previously, where we're trying to predict a phenotypic variable, for example, or some label unrelated to F, hopefully. Yeah, it's like this is our Y prediction task that we want to be invariant to F. And the common way to do this is to just make this a two-branch network and have S have an adversary. So we're going to train some network to try and predict S from Z, and then we're going to try and make that adversary as bad as possible. We're going to flip that loss and maximize the adversarial loss during the primary step of the training. So the most recent time this has come up is Benignin et al. And she et al. From 2018, 2015 with domain adversarial neural networks and their variant applications of it. But it's a common idea throughout the literature. And it turns out that this is also doing mutual information minimization. So we want the best of all adversaries, the infimum adversary, and we want to minimize the cross entropy, so the best prediction of S, right? This is the adversarial training step. And this can turn into entropy. And if we add a constant, so this is minimizing the negative of the Z loss, well, we can add this constant, and this turns into minimizing the mutual information. So this is actually the same thing. But the problem with this is if we don't achieve the infimum, so we don't have the best of all adversaries, then we have this sort of term, and this inequality should be over here, but essentially we're on the wrong side of the bound. So adversaries can do this if you train them well, but overall, if you don't train them well, or if you don't train them to this infimum state, then you won't receive the correct information, the correct gradient information. So you'll be minimizing something that isn't actually an upper bound of mutual information. So we showed this on an algorithmic fairness data set. I want to caveat that these results are now out of date because many people have published on them, and you can make adversaries better, but the result from the paper looks like this, that the Shi et al. Paper and the similar variational fair autoencoder, as you increase adversarial hardness, they don't actually stand up to harder adversaries. And this is mainly, in our opinion, based on the training method. So later we followed this up and showed that you can use adversaries, and they're much more general, but you need to tune the critical index. So you need to give the adversary, in this case, not in GANs, but in adversarial invariance, you need to give the adversary a lot more data than you do the main training step. Adversaries are actually more general though, right? You can put a predictive neural network on a lot of things, and they're sort of easier to set up, easier to tune and debug. So This is not to rag on them. And in fact, I've used them quite often. And in that loss that you saw in the previous slides, there was an adversarial loss on the data side. So they're not a bad thing. It's just that they're on the wrong side of the bound. So if you use, for example, the gradient flip trick from Guinan et al., you'll end up with undertrained adversaries and thus the wrong bound. Great. So this is the last vignette I have for you, and luckily that's good because we only have 8 minutes left. But let's talk about some of the problems of invariance. So why is this not everything, essentially, right? Like, have we solved the problem? And this is another restatement of this invariance model. We're going from data to invariant representation Z to label Y, right? And we want it to subject to this invariance constraint, Z independent of S. But if we do this, then the best that the model can perform, so if we achieve Z independent of S, then the worst site mediates how well we can predict Y. Essentially, the least informative site about Y bounds how well we predict the rest of them. This is sort of hard to prove in multi-site cases from the constructive side, so we can't actually form this statement, but we can arrive at it using proof by contradiction, right? And what does this mean? This means, well, first, it looks like a lowest common denominator effect, that if we include a whole bunch of sites, the one with the lowest SNR, right, the lowest signal, determines how well we're doing. So we can never do better than that site. And the reason for that is if we did better than that site, then our representation would have more information than that worst site. So it wouldn't be invariant, right? That's really bad. It's also related, yeah, it's related to how well we remove site signal. So if we really push down on this invariance criterion, then we force this to be true. And it's not clear how the dynamics of that go. Can we allow a little signal through? Right, this result is from last year, so we don't actually know. But if you have a null site, so somebody gave you knees instead of heads, and you're trying to do neuroimaging, but secretly the site from, I don't know, Duke or UCLA gave you a whole bunch of knee scans, you can never do better than 0, right? Unless you find out that they gave you bad scans and remove them from the data set. And worse, you can't predict anything in Y isn't in your shared support. So in the predictive set, that's included in all the data sets. Because if you could, that would include information that's specific to only a subset of the sites. And now Z isn't invariant to S, right? And so that's another problem. So yeah, this worst scanner syndrome also appears. It's the second half of, or it's the double-edged sword of invariance. And results like this also have started forming in related fields. So in fairness and differential privacy, there are similar results about impossibility theorems of how well you can do. So should we still do this? Should we still harmonize our data? And the answer is definitely yes, right? Because if you don't, you mix different data sources and then you learn about which scanner your data came from. And we know that going into different MRI machines or different X-ray machines or different measurements don't actually cause different labels. They don't cause different diseases, or at least we really hope not, right? So that's causally backwards, and so we should still do this. But the other cure to invariant representation is difficult. It's augmentation and forward modeling. So it's a lot of physics. So yeah, basically we're going to have to remove low signal data sets. So using every possible image is not the solution we want. Right, and we have 3 minutes left. So just to wrap up where we've been, invariance is caused by compression and conditional reconstruction. That's the main intuition here. Oftentimes, it can be helpful to lose the Gaussian encoder part of the VAE. And this brings us into this sort of alternative way of thinking about autoencoders, that instead of recovering latent variables that previously existed about our data, instead we're encoding them. And this brings us into the encoding literature. So Shannon and rate distortion and channel capacity and things like that. And to me, that's a very exciting place to be. We can try and build representations using this coding framework. So like finding anatomy or finding basically clusters of regions, parcellation, as the most descriptive set for our data, right? This doesn't really work in the cortical anatomy because we have really strong beliefs about it. But in white matter, for example, where it's much harder to find anatomy, this is something that we can work on, or if you're interested, we can work on it together. Yeah, that we should learn the anatomy from the data and not from outside sources, so dissection, because at some point our images will have different information than the dissection do, and we have to trust ourselves to believe that they're relevant to the underlying real anatomy, right? The living anatomy of these brains. Yeah. One really common question that comes up: why do we have to map between the sites? Can we just find a site that is like site agnostic? Can't we just choose the site agnostic image? And yeah, and alongside this, can we look at the Z encodings and interpret them? And I guess my answer to this is probably no, because there's probably never been an image that hasn't been taken with a camera, or in this case, an MRI machine. Like all the MRI images we've seen have MRI machines. So yeah, it's unlikely that the quotient over the site variable S is still an image. You can interpret these encodings, and of course, the previous slide was suggesting that we just interpret these encodings. But if we do this, we have to remember that it's up to the decoder. So if the decoder is very complicated, suddenly these encodings could be deceptively simple, that they would hide a lot in them because the decoder is storing a lot of this information. So yeah, interpret your latent variables responsibly. And yeah, moving forward with the invariance work, at least, we need to find a way to move past this boundary, this domain generalization problem. So instead of generalization, maybe we move to domain understanding, or talk more about site information. We didn't really understand, we didn't talk about how much we know about sites. We just used it as a one-hot S variable, right? Kind of abstracted to get across it. But we could do a lot of modeling there. And yeah, that's all I have for you. Thank you for listening. And do we have questions?
Thank you, Daniel. This is fascinating. Yeah, we have 15 minutes for questions now. Hopefully, like there will be some good ones. I can start if there people are not ready to ask questions. So one question is about the variations that we are trying to model, right? Scanner to scanner. Are these variations really because of the model of the scanner is different from one site to another site? Or if you have the same model from same brand, everything is same in two sites, we are still going to get some mismatch within them. I want to try to understand, like, to get to the bottom of it, right? What is causing? Of course, the cause is coming from physics, but like, what are the causes? And can we do a little bit more on like going toward modeling the physics, right? Than just, as you said, instead of a one-hot encoding, maybe like the physical parameters of the machine should be in S. Right. You know, like something like that. Yep.
So I guess a couple of things. If we have exactly the same hardware, there will still be a variation between the magnets, because the magnets themselves have to be recalibrated every every year or so, depending on the amount of usage. And they undergo something called hysteresis. So basically, every time we use it, we slightly add energy to the magnet, and so we're changing the magnetic field of the scanner every time we use it. Also, the coils, like there's mechanical and electromagnetic stresses and fatigue, so they will also change. So the receptive fields of the scanner will change over time. This is called scanner drift, and it's a well-documented problem in MRI. So there's these long temporal studies, decades, where they use the same scanner very carefully, and so you can measure the scanner drift and try and correct for it. And people do measure it using physical phantoms. So I think that's probably the best answer. It's basically talking to somebody in View IIS or talking to one of the great MRI people here and working on measurement of this problem and then modeling of it. So on the modeling end, this would be incorporating something like a physical model into QZ given, or sorry, PX given Z, the decoder, right? And this has become really popular in NERF, in these neural radiance fields. This is the rendering function. Well, here it would be a rendering function for MR. So I have seen a few of these papers. It's difficult to incorporate, and it's difficult to make it fast and differentiable, but you could imagine doing this for magnetic fields. The problem is, one of the main problems is that we don't really have great measurement of it in the first place. And of course, technically it changes by scan because there's something called shim coils, among other things, that each scan will have at different settings. So if we were to track all of that, perhaps we can do it. And I think it is possible, but the current data sets will not allow for it. So it would be a prospective sort of thing. Yeah.
Great. Any other questions? I don't want to hog the question time, but it's like maybe a relevant question to that. Like the role of augmentation was kind of like, I didn't get it exactly. Where should we care for augmentation in this setting, right? Do people do augmentations for different scanners? Because I mean, if you have data from these different scanners, great. But like if we can kind of generate potentially lookalike images from the other scanners, that will be helpful, right? Like to make our representations invariant to different scanners. Have people looked into augmentations for this?
I think, yeah, the answer is again, yes and no. Yes, because we have great MRI simulator, or great, we have pretty good MRI simulators. It's difficult to do because it's very, basically all the factors are entangled because of the magnet. But we have MRI simulators, and you can create data from different conditions. So that's really good. Here, augmenting our data would mean taking a data point from one scanner context, which is possibly unknown, and mapping it to a new one. And so it's easy to go downward, so to noise it up and to remove SNR, but it's difficult to go basically around the orbits or upward to higher, well, it might be impossible. It's likely impossible to go upward to higher SNR contexts. So yeah. So in that case, yes and no. We can augment, but most of the augmentations have not been helpful for these site-wise variances. Another thing that isn't really talked about, but perhaps should be, is that a lot of these site corrections are basically covering for label imbalance within each site. So in these large multi-site studies, we might get a site which has mostly positive or mostly negative cases. And so by learning the signature, there's a lot of information about Y, the label, in S, right? That's a problem. So it's not clear that we can really augment that away, unless we really could trust the augmentation to remove all of the site information. Yeah, so we would need a very strong augmenter. Yeah.
Fantastic.
Well, there were good questions along the way, so maybe we got through all of them. This has been
awesome.
Good.
Great. Yeah. So okay. If you may, like, let's unmute and thank our speaker again. Thank you, Daniel.
Thank you for having me.
Yeah, and see you in the fall.
Bye.
Have a good one. Bye.